Okay. So thank you for opportunity to speak here. I should start by saying that I'm reporting on 2 experiments involving a lot of people. I put their names on the slides. I'm not no expert in machine learning. I'm a positional number theorist. So I'm going to try to give my perspective from number theorists and what the experiments are about. Experiments are about L functions. L functions play a key role in this Langlands program. Not going to be able to tell you what Langlands program is, but I'll start by the most canonical function that we know of to give you the idea of the importance that it has in mathematics, and then we can delve more into what we learned. And the most canonical one is the Riemann zeta function, and this goes back to 1700s. I'll introduce it. Chebyshev looked at it first time to get a distribution of primes. Riemann was the first one to look at it and be like, maybe I can look at it not as a real function, but as a complex function. And in particular, as the way you write it only converges for like real parts bigger than 1. But then with the functional equation, you can extend it to the other half. In particular, the key part of this thing is exactly the functional equation. The functional equation is what enables, gives the full power of the Riemann zeta function. And that leads us to Riemann hypothesis, which is about the zeros of this function. And the upshot is that if you know the zeros of this L function, this Riemann zeta function, then you will know the distribution of primes on the nodes. So I could give you a whole talk about this. I'm not going to do this today, but the idea is like when you think about, let's say, L function, you should think about something that plays a key role for something that plays a key role for some arithmetic object, as the Riemann zeta function does for the integers, or to tell us about the primes. In particular, so the Riemann hypothesis is one of these $1 million prizes. So it's a challenge that's still here. And so in all the L functions I'm going to talk about, in general, I have the same kind of hypothesis attached to them. So I still don't understand very much about them. So that's worth to explore them. So let me tell you what the properties that you need to keep track in your head today. L functions have the Cauchy series. In our case, the Cauchy series of the Riemann zeta function basically all the ANs are 1. What we want here today is going to be, we ask us some like multiplicity condition. So if you have A and M, so n times m, where n and m are coprime, then you can write that as am times am. It's called multiplicity 1. So that's one of the properties. In particular, for me to write this infinite series, I just need to know the ANs at prime powers. Then the second thing, which is the culprit of the whole thing that makes it all work, is the functional equation. Now I'm giving you the functional equation here, and the particular part of the particular equation does not really matter that much, but I want to tell you some invariants show up, particularly like because how they affect like what I call the arithmetic complexity of our all functions. So the first one is n, that we call the conductor. In some ways, like, we believe that if you enumerate all L functions with certain parameters up to n, that's a finite number. So as n gets larger, there are more L functions. So this is one way you can think about arithmetic complexity. The other, I see it's very faint. The other one is the root number, this epsilon. Generally, it's like a number with norm 1 complex, but for today, it's just plus or minus 1. And that tells us some parity, like when you think about, it tells some parity about the function, some symmetry. And then there are things like the multi-equate or the degree, which I did not define on the slide. So basically, there's a way to measure complexity of L functions. So one of our goals is trying, like, let's look at a sample of L function of small arithmetic complexity and see what we can see. Where do we get them? So we're lucky. There's a old database called L function model forms database. It's much more than L functions. It's really about the Langlands program. And the key part is that when you think about L functions, you really think about it as a very, very good hash function for number theory objects. So it's magically will contain a lot of information. We still don't understand completely how, but that's why there's a whole database about it, because basically sometimes you have an object from one part of number theory to another part of number theory, and magically they're connected by the L function. So that's why there's this database about trying to show these connections. And in particular, there are some couple of things I can tell you about what L function know. Now, I'm putting some formulas on the board, and I'm sure like maybe for some of you already scare you. The point is that if I start with some object, for example, a number field, then the magical thing is that by trying to get what I'm really doing here is like getting the residue of this L function because of the pole, then I get things like regulator, class number, discriminant, all these things that are fundamental invariants for a number field. So it's kind of magical that shows up there. So this is a theorem. And another $1 million prize is the Burst-Identity conjecture, which now we start with elliptic curve. And you try to do the same thing. You try to look, now there's no pole, just try to evaluate the function. And what the conjecture tells us that the order of vanishing of this, I forgot S equals 1. The order of vanishing at S equals 1 is going to be the rank of the elliptic curve. And indeed, if you look at the Taylor series at 1, you get again some very nice invariants, which again not play a role for us today, but the idea that these L functions really know a lot, which is kind of magical. And more interesting, like there might be many elliptic curves with the same L function, and these quotients are the same. So it's quite surprising what's going on here. So let me first tell you a bit what's the idea behind. So as a number theorist, I would like to approximate this L function. It's an infinite series, so I cannot really just put on my computer an infinite series, so I need to approximate it. So natural questions like, how many AMs do I really need to approximate my L function? So theoretically, I know if I fix a family of L functions, then I need about square root of n. So in some ways, again, you think about this like this n as like somewhat the measure of complexity. So if my complexity grows, then I need more and more AMs to get the invariance of this L function on nodes. For example, competing invariants I showed you before. Now, heuristically, we do not believe that's the case. We believe that many things can be deduced with much less. So many people have tried to do this before. They have tried to guess certain invariants about L functions, but usually they focus on a certain class of L functions. And the question is, do you really need to focus on a certain class of L functions? Or should we look at L functions, like complex functions with certain properties, and what can you guess about them by just using a nice approximation, like a small approximation? So that's where we went with our first experiment. In particular, we focused on rational functions. There's some reasons to do that, but in some ways, a nice class. They're not all L function because there are too many, but rational, something you have a nice data set, you can look at it. So let me first tell you about our data set. So we just took 250,000 L functions from the database with small arithmetic complexity. And you can really see that so I'm here showing an upset plot. So basically, where it shows that all these L functions, where they come from. There's like the kind of the labels that tell you the kind of object they come from. And you can see there's a lot of overlaps. This is kind of what this LMFDB, this database is about. So I'm trying to show these overlaps, that certain things come from different objects. But in particular, I want to point to you that there's some dominant sources of L functions in our class here. For example, ECNF, which stands for elliptic curves or number fields, is quite dominant. Like more than half of them, or about half of them, can be described as coming from elliptic curve or number fields. But then there's like also other things, for example, genus 2 curves over Q, which are basically in this data set are almost very isolated. They come here alone, and then there's a couple more times that they come here that you barely see the plots there. So there's some connection there, but our data set is a bit skewed. And one of the things I'd like to do next is like trying to expand the data set and make it more homogeneous, or try to see if the origin really plays a role. So the source of this L function. But the best part is that we can just look at this data and like ignore the origin. And so the first thing we really care about, like motivated by like something like the Burst-Identity conjecture, is like the vanishing order of the L function and special value. So if you do that, you can start by doing some principal component analysis, where I see some separation. So our data was like we give the APs for the first one for the prime to 100. So we didn't give all the prime powers, the APs, and we did some simple principal component analysis where we saw some separation. Now, this is very similar what some of the people observed also, which now is known as murmurations. But so it's kind of, but I'm gonna let Kyu-Hwan talk about that later on. But the idea that it's already surprising that you get already some separation with just 25 coefficients. So I'm just giving 25 coefficients already get some separation. And so you can wonder why. Because from my perspective, in some ways, these tools are very good to show you some patterns, some correlations. And me as a mathematician, and my job is trying to figure out this correlation where it comes from. Now I'm going to show the next picture, basically the same plot, but in 3D, you really can see that the first component really has a lot of information, but the third component does not so much. And indeed, if you plot how much gain you get for each component, you can see that a decrease in information with time. So how many components you add. So given these and given that what we know, what's in another class of outcomes, particular suitability curves and other classes, it's natural to try to plot the APs and amortize them in some ways and group them by order of vanishing. And when we do that, we get this pattern. So the plot itself is not relevant. What's going to be relevant is when I click to the plot and I'm going to change the data set, you're not going to change much, you're going to see much variation. So this is like I'm plotting these average APs for all the functions, and I'm coloring them by order of vanishing. And now if I for example, I only focus on primitive L functions, then you don't see a difference. Like it's very hard to spot what points changed. And then if you like, okay, but maybe now you told me in the beginning that well, half of them came from the cardinal fields. Can you remove those? And then you do something again, like the plot, but it changed a bit, but slightly. So in some ways, this shows like, or at least to me, heuristically shows that there's a pattern here that does not depend on the origin or the source of the L function. And then I can try to do this again and like just remove the letter sort and ask to be primitive again. And then again, the dots show I'm getting less and less data, so that the plots are more erratic, but I still see the same pattern. So this leads to believe like, for example, can I try to guess the order of vanishing by looking at APs? So that's what we try. We try to train a neural network and try to get the order of vanishing. And particularly here, we plot the train and test the accuracy, and also plot the accuracy, the saliency map for our APs. And you can see, interestingly, smaller APs play a bigger role. Not all of them, because for example, A2 seems to play a much smaller role than A7 for some reason. I do not know. But more importantly, what we could ask ourselves, like, oh, I focus on these coordinates, what I call AP, but we know this principal component analysis will show us that I should have looked from other perspective. So if I shift the perspective and look at the coordinates of the principal component analysis, then we can see that the first principal component is really the dominant one, and we get basically the same accuracy. Yeah.
Just a kind of very naive question. I mean, these are analytic functions, and so like the naive model would be expanding on something. The rate of growth of coefficients will govern the strength of the leading as you know.
So I should say that I'm here hiding my number theory background, which I'm trying to normalize things in a way that.
But is that not a good way to think? Or are you trying to get comparable things? You're trying to...
Yeah, I'm trying. Like they come from different sources, so even the ANs grow at different orders of magnitude. So in particular, we need to normalize things so that they all behave the same magnitude. Otherwise, one source might dominate.
So these are all normalized so they're on the order of square root p, right?
Yes. Yeah. AP is about square root of p.
So you've taken that out.
I took that out. Yes. In particular, is I can be more precise. Like let me just take the magician hat away. Like if I for example, if I look at these two plots here, the blue and the red, they basically differ by sign -1. So if you flip that, if you make the order of vanishing play a role, then you see them overlap precisely on the nose. And perhaps that's what you should do. But then surprisingly, that doesn't happen with order 3 and 2 and 3, which is very confusing. So that's a thing we should investigate further. But you know, we're expecting that to happen. The 0, 1, and 2 and 3 do all overlap if you correct by the right side, but that can happen surprising. But as a plot, it's better to show the data separated.
Yeah, I mean, you still could imagine it's, once you make this, you say like this is kind of something growth factor that you're looking for, but it's not like a simple conjecture like that.
Yes.
Yeah, okay.
Yeah, that's certainly true, and I think we worked on this a bit, but we have not explored the data completely. In particular, the thing you should do is like try the same experiments over and over with the same data, with different origin, and see how do they behave drastically. So if they behave drastically or not, that's the thing that I would like to do, to figure out if what's indeed the behavior underlying this, because the data set is a bit skewed, so we should be careful. I think one more thing I want to say about this graph, like when you look at personal components, you get clearly the first personal component playing the bigger role, but Yidi indeed trained is just on a first personal component, and basically the accuracy was very similar. Like by 1.5 epochs, we were already above 80%. So it's quite surprising that just looking at the first component, you get such accuracy.
What's also surprising is that this saliency identifies PT24 as the second most important one.
Yes. No, that's there are many things that are surprising, but again, I think that what I struggle with is that as a mathematician, that this is very interesting. Like I think the point is like the first one is always that's winning. The 24th, it's not to me too obvious. I don't know how much noise is in the data.
Yeah, the thing is, like one case where you do the PCA, you'll find out like even for PT24, it still explains a lot of the difference in the data. So like PCA here doesn't really give you too much in the dimension reduction. So if you can compile, there's another plot in our graph. Basically, you can see how much variance each PC can explain, and you see that you actually need all 25 principal components to explain the like at least 95%. So even if it's PT24, it doesn't mean it's like a weak.
Yeah, maybe the first way that I think about is like if you think about the step, it's like there's a big step in the first step, and then there's like a linear. Yeah.
The PCA is only going to see linear stuff.
Sure.
I might think that like some Laplace transform basis or something would be one.
There are many things to explore, but I think my claim so far is that things do seem to behave nicely independent of the source. So, which is
universality between all functions.
Yeah, I think it's about like sort of like focusing on like elliptic curves, which are like attached to the BSD conjecture, attached like these famous problems. Maybe you should go a bit deeper, like L functions first. They're a connecting point. That's what we're getting there. So maybe you should look at them all together instead of focusing on one class. Or maybe you could learn from other classes what people have done and see like, can they apply the same techniques or not? There are many things to occur, but so far, from my perspective, so these are my own words. If you normalize data set in the right way, it's like doesn't matter what right way. Then we get the same kind of behavior across the whole data set. And in particular, for example, there were subsets of our group. They tried to do like linear discriminant analysis to get stored or vanishing, and then observe that in some data set. So it means that we now should be trying the same exactly approach on the whole data set and see if it also works. So there's many other experiments that have been run before us.
But what does that first component look like just as a function?
What's the first component? I do not know. I think that's the thing that I would like to look, because that's exactly.
The computer knows it.
Yes.
It's probably just loaded with smallest primes, right?
Yeah, but it's got the biggest weighted A7, which is crazy.
But I think that the key part here is not for me, is not like you don't look at this data set and you fix it. Like you look at first very small complexity and you see what's you need to see all this projection to this one-dimensional vector space changes as you keep adding data. So to conclude if there's something there, or you're just being lucky, right? Maybe I was so lucky that the data set is like, but if I go much higher complexity, then it's all messed again. And I need to do another, because okay, I've done this experiment before, and that's what I saw. Like sometimes you're like, oh my God, found gold. And then you double the complexity, and like my original projection was nothing. Now it's all noise again. So
well, I mean that's definitely the thing you should look at, is how it depends on the size of not just the size of the data set, but the number of coefficients you take. But if it varies, it might be that it's like some nonlinear feature.
Yeah.
Just made the best linear approximation to it or something.
But the fact that something there is surprising.
Yeah, okay.
But conclusion for me is like they seem to be agnostic of the source. It means that you can apply, instead of focusing on one classical functions at a time, you should perhaps focus on all functions instead at a time, at least rational ones. And maybe you need to add more objectives, but we don't know yet. And so, but on the other hand, the dataset is quite skewed. So I think that's why I put the upset plots. It's easy to get very excited about this, but then realize that the dataset is really skewed in some direction. So we should try to make dataset more homogeneous, or look at the class and see if things really behave the same way. Now, I'm running out of time, so and I still want to have a more story to tell you, which is now that we have these, you like to apply the same techniques to other L functions, because like I already told you, like nothing doesn't depend on the source. So one thing like can you apply to non-rational functions? And so these introduce to a data set called Maass forms. Maass forms are complicated, so I'm going to try to summarize them in a single slide. It's just like a more complicated version of classical. And now you're like, what are classical? It doesn't matter. The word classical means basically people have been studying this for centuries, and Maass forms are more like latest like a century. Let's put it this way. So it's a more complicated version. Many things change, but many things are the same. In particular, what I wanted to focus on is that L function looks exactly the same. Computing L function, for people that know the theory, will be like, oh, it's boring. But for Maass forms, even if you know the theory, is complicated. So that's the point. Like it's hard to compute L functions, but you have a set of them. With about 35,000 that's been added recently. But unfortunately, for you to run the same data, you're missing some. If you like to run the same experiment, but you're missing some data. So maybe the tool could be like, can I look at them the same way and try to guess that incomplete data? Because I'm running out of time. I'm going to just dump the whole slide in one go. So the idea is that there's this functional equation, an extra functional equation on top, and there's this fc equals f minus 1 over nz up to a sign that's always plus or minus 1. And that we don't know that for half of the data. And in particular, imply that for all the primes that divide the conductor, this end, we also do not know them. So for some of them, we really are missing a bunch of data. And you would like to do that. And once again, the functional equation tells us that if you compute enough of them, this data is there. But it's very complicated to compute enough of them. So we would like a more practical method, which is try to guess this plus or minus 1. And on my last minute,
Oh, you started a little late. You have 5 more.
yeah, okay, I'll try it. I'm going to slow down again. Thank you. So we can try the same thing again. We expect this kind of wavy experiment again that we saw before. Now we just like ignoring the order of vanishing. We just look at Fricke sign. That's a thing we do not know in half of the data. And we plot it, and we're going to see some kind of behavior. We're going to do the same trick as again as like averaging over at every prime. So even here, we can already look at the data and be like, maybe linear discriminant analysis will be a good candidate to try to classify data that's missing this information. And things get a bit better if you again try to add some more mathematics to the data. Like you know some structure about it. Particularly, there's this thing called parity. So if you or symmetry type, that's what I put on the slide. Then things separate even better when you normalize by that. So now we're really screaming at you that you should try to linear discriminant analysis. And indeed, if you focus on one type, like odd, so now to be clear that these are all known yet. Now I'm going to focus on one type and things get a bit more. So now I focus on half of the plot as before. And now the gray things are the things that were unknown before. And you now can see the guesses. And they match the data that we were given before. So in some ways, like it seems it's a good candidate to try to use linear discriminant analysis. In particular, we still want to test, at least compute for some of these L functions to see if you are right or not. Like on the test data, it performs very well, but we also like to know for this, the ones that we don't have. Because the ones we don't have, the data is because it was hard to compute. So maybe there's other pattern there why it was hard to compute. Maybe we're all completely wrong. We don't know. Because we're biased, we're survival bias, because we only have the data for the ones that was easy to compute. And more surprisingly is that one of our collaborators, inspired by these, he went to train some neural network, and he picked it from polynomial. He picked like the magnitude of the gradient, and he showed like where things play a bigger role. And I would like you to like clearly again, small AP. So this is my index. So small APs are here, small primes are here, but the last one has a very high magnitude. And you might be like there's something off. And the best thing here is that is a way that maybe sometimes you should apply. I think machine learning tools like you don't tell them the whole information, because the last parameter is not an AP, is the eigenvalue of the Laplacian. So that's what makes math forms important. And from that eigenvalue, you can almost deduce everything theoretically. So what we learn indeed, the eigenvalue of the Laplacian, which mathematically we know we can deduce almost all the information, is the one that's playing the bigger role. So that's quite surprising. So indeed, I think that the next experiment is really trying to compute the things rigorously, even if it takes like a couple of years of CPU time, and then verify that we're correct or not. Because even though that the first prime seem to play a bigger role, the eigenvalue is playing a bigger role even, which is surprising. So in some ways that, by the way, the eigenvalue also shows up on the L function. I didn't say about that, but it's very surprising that there's this disparity, and the neural network picked up the signal from the eigenvalue, even though we didn't tell it about it. Particularly, we didn't tell Giorgi about this. So in some ways, it's surprising that that shows up there. Because if I trained the neural network, I'll have thrown that away. So in some ways, it's nice that you included it. We observed it. Okay, I'm going to stop there.
Thanks.
Doesn't David Lowry-Duda have guesses for some of the ones that are unknown based on numerical approximations where you just can't quite prove?
I think that's what I believed in. I think the claim is that the server where the data was is now not with us. So I think we again, and I think again, one can compute it by computing invariants, and I think that's the issue. Like, oh, so I'm trying to convince David Lowry-Duda, which is one of the collaborators, to compute the data, because that's the thing. That's the thing, because there's a survival bias here. Like we don't have the data because of hard compute, so maybe it does not really behave as the data that we have.
But what accuracy did you get on your classifier, your predictions for the cases where you were intentionally removing data, but you actually know the answer? I mean, it looked like I could get like 99%.
I do not know the numbers. I do not personally care about the numbers. Like it's high. That's what I care. It's like I think it's maybe in our draft. I don't know.
It was not 99%. Remember, it was about 90%.
90%.
To be honest, I was not quite. So the domain model that you were talking about, you're predicting the order of
vanishing, yes.
And the PCA was just on the input, so the PCA is usually
yes.
And then you were using that to classify by a linear thing or by a neural network, or how
So there are two kind of things. So there's let me just go back. You look at the PCA for the cluster for there's like all rational functions, big set of them, 150,000. And the question is, can you find some machine learning method to guess the order of vanishing? And obviously, you can look at it already. So like maybe I can already do very good predicted by hand, because the things are really ordered like 0, 1, 2, 3, 4. So it's already a good guess.
But your classifier, it's just
I think so. Again, hard to me to say what everyone did, because I think many people did many different things.
Yeah, so the classification was done by a neural network with AP first, and then with PCA.
Well, what did you do with the PCA?
So first we did PCA, and you eyeball this frequency separation, and then we train that with a neural network by using the principal.
Yeah, as inputs to it.
Yes.
Yes.
Okay.
And I think you also did the thing which is just look at the only one component.
Yeah.
And still,
I don't know one.
And for me, it's the more surprising that you get 80% on the nodes. So basically, just projecting on the first.
Because I mean, there's some naive sense in which the problem is linear, right? If you just took linear superpositions of these functions, and
Yes.
instead of predicting the order, you predict the coefficient of each of the
Yes.
powers.
So I think the whole question here for me as a putting my theoretician hat is that when I increase the complexity of the data, how does this prediction is gonna do? Or like, because in some ways, like I do not know, as I said, like sometimes you do this like let's say prism component analysis, you really nice separation, then you increase your data set, and now the things got rotated or mixed. And once again you have so it's hard to
Oh, yeah, for sure, you gotta study that in depth. I'm just trying to step back at the math of the problem. I mean, maybe there is just some sort of correct basis.
I don't think that's correct. So the key parts, this is like let me just go back to a couple of slides. The key part is that these things are defined by these ANs, and these ANs have multiplicity. So if you know A2, you know almost half of the primes. Sorry, half of the ANs.
Well, you say that's not linear, multiplicative relation.
Yes. So you know if you know A3, then you know a third. So in some ways, you know that the first ANs are going to play a role, the first APs, or because there's a multiplicity condition. You need like I can tell you that I've done this before, but I don't have a picture here, but I can make you visualize. Here we looked at primes, APs, and I think you also did this in some paper of you like just look at ANs. And then what you're going to see is that you're going to see these like very nice blobs of data, and then you ask yourself what are the blobs of data? It's basically telling about multiplicity one. It's telling grouping things about what's the value of A2, A3, A5, because this like most numbers are smooth. So that's the thing. Like maybe there's something else there, but I think the first primes playing a bigger role, I think it's kind of expected.
There's a thought for why A7 might matter. I bet a lot of the L functions have good reduction at 7, but bad reduction at 2, 3, 5.
Yes, in particular,
why A7 is giving you more information.
In particular, if you go back, the overnumber field and the discriminants are 1 or 0 model 4, and those are always in the conductor. So half of them we're gonna have bad reduction at 2. So there's all these things that one needs to be very careful before we jump on.
That's to me now that A7.
I don't know, A3 is there still, and where's A3? Okay.
What proportion of the data set was imprimitive?
Very small.
Yeah, so I would be, I think the difference between just keeping primitive and keeping everything.
No, I think it was like 20% were imprimitive.
20% really, because I would expect these things to look quite different for the imprimitive ones. Certainly for the murmurations, they'll completely disappear.
I don't know, I need to look at the data again.